if we're going to have a problem-solving kind of day, then I will post a lecture video beforehand, at least a day beforehand, so that you can take some time to review that, and then we'll solve problems when we're together in class. Okay? So today we are going to spend just a little bit of time going over chapter 1, some of the later topics in chapter 1, including units and sig figs, and starting in on dimensional analysis. Because we're talking about dimensional analysis today, tomorrow in lab, we will take some time and work through a few dimensional analysis problems, see how far we can get working up to some more difficult kind of problems. For Friday's lecture, we'll start in on chapter 2, and so do expect a lecture video to be posted either this afternoon or tomorrow morning for lecture 2 stuff, chapter 2 stuff. That lecture material will lead into some problem solving that we will do for class on Friday around atomic structure and around naming compounds and starting to talk about isotopes and things like that. All right. Any questions before we get going with chapter 1 stuff? All right. I don't see any hands. I haven't muted you, so if you do have a question, feel free to just unmute yourself and holler out, okay? I'm going to share my screen and we will get going. All right. So in chapter 1, it talks about a little bit of background in chemistry. And even before that, a little bit of background in matter and things like that. This is part of the reason why I like ALEKS so much. It has told me that the vast majority of you knew the difference between a solid, a liquid, and a gas, and things like that. And so I'm going to just fast forward through that. One of the topics that it said we needed a little bit of help with, based on that initial knowledge check, which most of you have completed, was the difference between intensive and extensive properties. Okay? To talk about that, I'm going to back up just a minute to talk about the difference between a physical property and a chemical property. Right? When we talk about physical properties, we talk about things that are unique to a particular compound, things like hardness, things like color, things like melting point, right? These are all physical properties. And then when we talk about chemical properties, we often talk about things like reactivity, how it's going to react with other elements or other compounds, and then sort of how the substance looks in terms of the chemical composition. When we jump into chapter 2, we'll talk about the law of multiple compositions and get a little bit deeper into that chemical stuff. But talking about physical properties, we're going to break these into intensive and extensive. And so an extensive property, that's something that the more of a particular substance we have, the larger that property is going to be, right? Sort of the easiest example of this would be something like mass, right? The more we have of a compound, the more we have of a substance, the higher the mass of what we have is going to be, okay? Who can come up with some other examples of extensive properties, things that are not based, things that are based on sort of how much we have? Sure.
Density?
So density actually falls into this intensive property. Because the density of aluminum, for example, is the same if I have a sheet of tin foil or if I have a part of a car body that's cast out of aluminum, the density of that aluminum is exactly the same. So density is an intensive property. It doesn't depend on how much we have. It depends on only what that material, what that substance is. And so density does not depend on how much we have, because if we think about density, yes, the mass goes up, but the volume goes up as well when we have more stuff. And so if the mass and the volume both go up, then the density doesn't change. But that brings us to another extensive property, volume. Right? The volume of something is an extensive property. The more we have, the more volume we're going to have. Anybody have any other ideas for intensive or extensive?
Could it be like, I don't know, if you're talking about it's like molar weight or something like that, like for the intensive, like that is a
Absolutely.
constant.
I'm going to call it a molar mass. That's just the way that I think about it. But yeah, absolutely. The molar mass of a compound, yep, is an intensive property. If I have 3 molecules worth, or if I have, 3 beakers worth, the molar mass is the same because that's going to be grams per mole. Going along with mass and volume here, we can also think about things like length, right, or area. These are things that are going to increase the more we have. Some other intensive properties, things that don't change, things like color, right? The color of a particular material doesn't change the more of that material we have.
Like, what about the, oh, sorry for
Go
interrupting
ahead.
you.
No, go ahead.
Like the number of protons or electrons, like valence electrons that it has for intensive?
Yeah, so that would be, that's more of a chemical property than a physical property. And while this doesn't say exactly physical properties, we think about that more as a chemical property. So I'll write those sort of over here, but I'll put the number of subatomic particles.
That's for the field of 1v1 intensive.
Say that one more time, Michael.
Like the feel of it, how it feels.
Absolutely. So when we talk about metals, we call sort of how shiny it is what we talk about. And so that's called luster. And so, yeah, absolutely. Some materials are sort of shiny by nature. And if you have a small amount versus a large amount, then that stays the same. Cameron, did you have something to say?
Would temperature be intensive?
Yeah, absolutely. Temperature is also an intensive property. If I have a cup of water versus a gallon of water, as long as it's in the same environment, that water is going to be the same temperature.
Would malleability also be one?
Yeah, absolutely. Malleability, talking about how much we can flatten something out into sheets. There's the ductile nature of things. That's how much we can pull it into wires, into strings. All those are intensive properties. And so just getting this basis of intensive versus extensive, that's where I wanted to go. That's where I wanted to start, since that's what Alex told me you were missing a little bit of in the initial knowledge check. Okay. All right, moving on into the bulk of chapter 1. It talks a good bit about this system of international units, the SI system. And so hopefully you're relatively familiar with this. When we talk about length of an object, we're going to talk about it in meters or in some unit relative to meter, like centimeter or kilometer. For mass is a funny one because it's not the gram, it's the kilogram. And actually, there should be a lowercase k. I think that's just an error in this figure. The kilogram is the SI unit. I don't know how much you keep up with news in the SI world, but about this time last year, there was a new definition for the kilogram. Previously, it had been this small block of an alloy of palladium and indium, and it was kept under vacuum, and you couldn't touch it with your bare hands. And they took it out and they weighed it once every 4 years to make sure that it was still a kilogram, and to sort of calibrate all the balances to be so that that little thing was 1 kilogram. It was the only one of these base units that was still connected to a physical object. And just last year, they managed to separate it from a physical object, and now they use the definition of a mole to talk about the number of atoms of a certain element. I can't remember off the top of my head which element they use, but they talk about a certain number of atoms of an element is equal to 1 kilogram. Time we measure in seconds. Electrical current in amps, we won't really use that one this semester. Temperature in Kelvin, we'll see both Kelvin and Celsius. The thing to know about Kelvin and Celsius is that the difference, the size of a Kelvin degree is exactly the same size as a Celsius degree, right? And so a difference of 1 degree Kelvin is the same as 1 degree C, right? So 1 degree C is equal to 1 Kelvin. Right? That's when we're talking about changes. Now, their 0 point is different, right? The 0 degree C is what? What do we associate with 0 degree C?
Absolute.
Is freezing point. Right?
Freezing point of water, yep. And then 0 Kelvin, Matthew,
Absolute 0.
is absolute 0, right? That's the lowest temperature can be. And that's a difference of 273 degrees. And so to get to our degrees Celsius, that's going to be, sorry, to get to Kelvin, let me think about this a different way. To get to the Kelvin, it's going to be whatever our degrees C are plus 273. Right? And so 0 Kelvin, then degrees C must be negative 273. And so absolute 0 is negative 273 Celsius. And then 0 Celsius is positive 273 Kelvin. The last one that we're going to talk about, we won't talk about candela. The amount of a substance in moles. We won't talk about moles for a couple of days, but that's the beginning of chapter 3. And we will spend much of the semester discussing moles and dealing with those. Okay. Any question on these units? All right, moving on to prefixes. This is much of what we will do tomorrow, working with these prefixes and making sure we know how to convert between them. I've sort of grayed out the ones that I don't expect you to remember. The others that I haven't grayed out, these are the ones that you need to know and you need to be able to use. Right. These prefixes just help us deal with really big or really small numbers. As chemists, we don't deal with single atoms or single molecules very often. We often deal with a mole of molecules or a mole of atoms, and that's 6 times 10 to the 23rd. And so we're even way above tera up here. You know, we're talking about yotta and zepta kind of prefixes. But when we talk about masses and volumes and things like that, a lot of times instead of having lots of decimal points or lots of trailing zeros like this, we don't want to use those. We want to use those prefixes so that it's a little easier to talk about things. The other option, of course, is to use scientific notation to talk about these really big and these really small numbers. But because scientists use both the prefixes and the scientific notation, it's good for us to know both of those systems. Like I said, we'll practice with this much more tomorrow when we're in lab. All right. So using units a little bit, let's do a practice problem. This is from our textbook. Practice problem dealing with density. A piece of gold has a mass of 301 grams with a volume of 15.6 cubic centimeters. Calculate the density of gold. Who can tell me, who remembers sort of the formula for density?
Isn't it like mass over
mass
volume?
over volume?
Absolutely, mass over volume. I heard a couple folks there. So D is equal to M mass over capital V for volume. And so we need to just plug this in. We have 301 grams divided by 15.6 centimeters cubed. Now, that centimeter cubed, is that really a volume? That seems like it's a distance, right? Centimeters, that's related to meters, that's related to measuring length. How do we get volume out of that? Well,
It's
it comes,
equivalent to a milliliter.
yeah, absolutely.
Sorry.
So 1 centimeter cubed, excellent, is 1 milliliter, right? We can think about it that way. The reason that length cubed is the same as volume is because if we draw a cube, and my skills as an artist are not great, but if we draw a cube, right, then we have 1 centimeter here, we have 1 centimeter here, and we have 1 centimeter here. To calculate the volume of that cube, it's just 1 centimeter length times 1 centimeter width times 1 centimeter height, and we get 1 centimeter cubed. And so, oops, that shouldn't be cubed here. But we get a volume from a distance unit or a length unit that's been cubed. And so this is a very good conversion factor to know. 1 centimeter cubed is a 1 milliliter. And so, you know, it doesn't tell us what units this density should have. So we can leave it either as centimeters cubed or as milliliters. It doesn't really matter. Who's done that math? Go ahead.
Oh,
Oops, who was it?
Matthew, go ahead.
19.29487179.
Excellent. So I am so glad that you gave me all those decimal points, because the next thing that we're going to talk about is sig figs. Right? How many of these decimal places are really significant?
like,
3.
yeah.
All of them? I don't know.
So
Wait,
not
yeah,
all of
3.
them. So whoever did these measurements, they were only able to measure the mass of gold. Oops. They were only able to measure the mass of gold to the 1 gram place, right? They couldn't go any farther than that. And so they only have 3 digits to describe the mass of gold. Same for the volume. They have 3 digits that have described the volume of that gold ingot, right? And so we don't know if it was really 15.562 or if it was 15.643, right? Those are kind of different numbers, because we don't know that because we only have 3 digits to work with. And so if we only have 3 digits in both of our initial values, our answer should have just 3 digits. And so we end up with a density of 19.3 grams per centimeter cubed, right? I'm pretty persnickety about elements, make sure, about units. Make sure that you follow your units through problems. I have a tendency to write things like gorillas and unicorns if you don't have a unit. Julia, go ahead.
So for this problem, could we have changed centimeters cubed to milliliters and left that as the answer, or would you like want it to?
That would be a-okay with me, absolutely. Yeah, if you had left this as 19.3 grams per milliliter, I am a-okay with that. Either way.
Also, when we're using Alex, I know it has like all of the formulas.
Should we be using those like what we may already use on exams?
My theory about that is that if it's a pretty simple equation and an equation that we've used a lot, I'm probably not going to give it to you, right? You will not see the density equation on a quest. If you get to ideal gas law, you're not going to see it on a quest. Hopefully we've used it enough that you know what that equation is. If we have more complicated equations where, you know, maybe there's a negative sign that you could forget or something like that, absolutely I'll give it to you. And of course I'll give you all of the constants as well. I don't want you to, you know, forget what a constant is and get the problem wrong. But the simpler equations that we use all the time, you should be able to know those for a quest.
Okay. So
All right. Okay, one more practice here. Now we have the density, 13.6 grams per milliliter for mercury. And I want to know the mass of 5.50 milliliters. And so if I know the density, again, D equals M over V, 13.6 grams is equal to some mass over a volume. I need to come up with a mass. Who's got it? Who's got it?
$74.8 grams.
There we go. 74.8 grams. Right? And so this is just remembering density, remembering your algebra rules, things like that. I just wanted to make sure we're all sort of on the same page with that kind of stuff, okay? All right. So moving forward, talking a bit more about sig figs, trying to figure out what things are significant and what things are not significant. When we look at a number, when we look at a number, any digit that's not 0 is significant. So if we have a number like 1,234, how many sig figs do we have there?
4.
4, you betcha. I'm going to abbreviate sig figs as SF usually, right? So I'm just going to say 4 sig figs. If we have some zeros that are in between non-zero digits, right? So let's say it's 1,204. Right? How many sig figs do we have there?
4.
14. Zeros that are to the left of the first non-zero digit, so something like 0.0, 1, 2, 3, 4. These zeros to the left, so that's both of these, are not significant. So I still have
4.
4 sig figs. Once we get to dealing with decimals, it gets a little bit trickier. And so if a number is greater than 1, all the zeros to the right of the decimal point are significant. Okay? So let's say I have 60.0. Okay. How many sig figs there?
2.
3.
So 2 or 3. We know 6 is significant because it says it's a non-zero digit. It tells us in this rule that all zeros to the right of the decimal point are significant. So we know that one is significant. That one in the middle is a 0 between significant figures. And so that one has to be significant too. Right? We will never have insignificant figures between 2 other significant figures. Right? And so this one has 3 sig figs. All of those figures, all of those digits are significant. If we have a number that is less than 1, then the zeros to the right of non-zero digits are significant, right? So the way our textbook words it is at the end and in the middle of the number. And so if we had a number like 0.00430, how many sig figs there?
3.
We have 5.
This one is just 3 because these 3 fall under this rule up here. They're to the left of the first non-zero digit. And so let me change colors here. These 3 are significant. Okay. The 4 and the 3 are obviously significant. And then because that last 0 is to the right of our last digit and it's to the right of the decimal, then it counts as a significant figure. So this last one to me is perhaps the most confusing rule, right? Again, the way that I think about this is that zeros right of the decimal and right of a non-zero are significant. Okay, that's just another way of thinking about that rule, a little different wording. Okay.
Question.
Yes, sir.
So somebody have 6.000, it'll be 4.
Absolutely, 4 sig figs. Right. What you're doing when you say 0.000 is you're saying, I measured it, and it's not 6.0, it's not 6.00, it's 6.000. I measured it that far, right? When we look at these 4 sig figs, that last position, that's the one of least significance. And so that's the one where we did any rounding, right? Maybe it was 6.002, or sorry, 0002, and we rounded it down. Maybe it was 5.9999 and we rounded it up, right? It's that last digit where we did the rounding. All the others are not rounded digits, right? Matthew, I see a hand.
If the number is just 1, would it just be one significant figure?
It depends, right? When we talk about significant figures, we talk about significant figures for measured quantities. Right? There's a difference between a measured value and what we call a counting number, or an exact number. And so if it's a counting number, then you're saying I have 1 beaker, right? It's one thing. I have 1 calculator. It's not 1.0 because I didn't measure it, right? And I just counted it. This is 1. And so counting numbers, or we think about as exact numbers, and they have as many significant digits as you need, right? They do not limit our number of significant figures when we do calculations. That actually shows up a little bit later in the slides. So let's practice a little bit. Thinking about the number of sig figs in each of these values. So who's got the first one? They're all non-zero. Julia.
Person has 3.
Rosie. Yeah, the next one. Just yell it out.
3,
3,
3. Next one.
3,
3,
Do the next one.
2,
2. The next one.
4,
4. Excellent. The last one.
4,
1.
4.
Yeah, so this one is just one sig fig, right? This one is a bit confusing. Let me roll back to our rules. Any digit that's not 0 is significant, and zeros that are between non-zero digits are significant. Right. And so if it's not between two non-zero digits, then it's insignificant. It's not significant. And so just the 7 there is our significant figure. Right? For numbers that are round like that, it can be a bit confusing. And so there's a couple of ways of dealing with this. If it is 7,000 and we measured it to be 7,000 with 4 sig figs, then I could write this as 7,000 and just put a dot at the end without adding any 0 after it, right? I don't want to add another digit, but I want to show that it's all significant. And so if we do it this way, that's 4 sig figs. The other way to do it, and the way that sometimes is less confusing, is to write it in scientific notation, right? What if this is 7,000, but only 2 of those digits are significant, right? It's actually 6,953, right? I'm going to round that to 7,000, but only 2 of those 4 digits are significant. The best way to do that is to write it in scientific notation, 7.0 times 10 to the 3rd. If we do that, then we have 2 sig figs. Right? The reason scientific notation is nice for significant figures is because the way scientific notation is formatted, every digit you see, by definition, is significant, right? So if you see 4 digits, it has 4 sig figs. If you see 2 digits, it has 2 sig figs. And so I'll make that note over here. In scientific notation, all digits are significant. Now this assumes that you're doing scientific notation correctly, right? You have to start with a number between 1 and 9. You can't start with 0. You can't start with something like 10 or 20. You have to start with a single non-zero integer, and then everything's based on that. Okay. All right, any questions on figuring out sig figs? We'll move on to sig fig math rules. Okay. If we do sig fig, if we're counting sig figs for addition and subtraction, then the rule is that the answer can't have any more digits to the right of the decimal point than any of the original numbers. So let's say I have 84.1 plus 3.67. Right. Adding those up. If I just do that addition directly, then I'm going to get 87.77. But according to this rule, I can't have any more digits to the right of the decimal point than any of the original numbers. And so I have to round this one. It has 1 digit right of decimal. And so I have to round this to the 10th place. And so what would my answer be?
87.8.
That's right. Okay. Now, the textbook talks about this as decimal points, but in reality, it works for any place. So let me give you another example with the same numbers. If I had 840 1,000 plus 36,700. Right? I'm going to add that up, and I'm going to get 877,700. But again, because this is the lowest place that all of my numbers share, right, then I need to round to the thousands place. And so I'm going to round to 878,000. That does just have 3 sig figs, or I could write it as this way if I wanted to be a little clearer about how many sig figs I should have. And so, again, our textbook says that it's the can't have any more digits to the right of the decimal than any of the original numbers, which is absolutely true. But if we're dealing with really big numbers, they can't have any more digits to the right of whichever place all of the numbers have an actual digit. All right, so that's addition and subtraction. That one is a little bit more cumbersome than multiplication or division. Right? In multiplication and division, it's just the lowest number of significant figures. Right? And so if I have 4.51, I'm going to multiply that by 1 2/3, so 1.66667, right? Because that number goes out a long way. When I do that multiplication, I get 7.51666, and it goes on a bit. But how many sig figs should I have in my answer?
3.
Yeah, I'm keeping the smallest number, so that's this one. So my answer should really be 7.52. Same is true for division. We're always going to round it to the lowest number of sig figs. Okay. This is what we were talking about a little bit earlier when we talked about exact numbers. If I have a counting number or an exact number, then that doesn't contribute to sig figs. And so in this problem, we're going to find the average of these 3 lengths, right? So 6.64 plus 6.68 plus 6.70, right? Divide by 3, that's how we find an average. This 3 looks like it only has 1 sig fig, right? But really it has an infinite number of sig figs because we're counting the number of lengths we measured, right? That's not a measured quantity itself, that's a counted quantity. And so that 3 is really 3.00000, as long as you want it to go, because it has many more sig figs than we need. And so if we do that, we get 6.67333, which we're going to round to how many sig figs?
3.
3.
6.67 is my average, right? Okay. Those exact numbers make sense?
So why do you round it? Sig figs.
Your microphone's acting a little funny, Griffin. Say that one more time.
Can you hear me?
You're still a little scratchy, but try it out.
Why do you round it if you can have an unlimited number of sig figs?
So this 3 in the bottom has an unlimited number of sig figs, but these on top do not, right? These each still have 3 sig figs. And so because of that, we keep, with multiplication and division, we keep the with multiplication and division, we keep the lowest number of sig figs. And so on the top, right, we have 3 sig figs. And on the bottom, we have infinite number of sig figs. We keep the lowest value, that lowest value is 3. And so our answer should have 3 sig figs. Okay? All right. Oops. So dimensional analysis. We'll put those put that work of sig figs to work now. So when we solve a problem using dimensional analysis, there's sort of the standard way that we do that. We figure out what conversion factors we need, and we got to make sure we carry through units. I know that it can be easy to drop units and get a little sloppy, but you won't know that you have the right answer unless you carry those units all the way through, right? So let's say that we want to convert 3.62 kilograms into milligrams. Right? We start with our conversion factor. And to figure out what our conversion factors are, well, we have to know how this initial unit and this final unit are related, right? And they're related through grams. Now, maybe you know the conversion directly between kilogram and milligram, but I'm going to assume that we don't. And so I need to convert both of these. I'm going to go through grams to get from kilogram to milligram. And so 1 kilogram is equal to how many grams? Anybody?
Is it 1,000?
It's 1,000, absolutely. Right? And how about milligrams? 1 milligram is equal to
0.001 grams.
0.001 grams, yeah. I'm A-okay if you keep this as 10 to the third and 10 to the negative third, right? If you want to keep it as decimals, fine. If you want to keep them as what we call factors, that's fine too. So now I'm going to set up this calculation. Maybe you call these railroad tracks in high school or something like that. I know that term gets used a lot. But we start with 3.62 kilograms. Okay. And now we're going to take these two equalities that we used, and we're going to figure out which one we need. Well, we start with kilograms, so we're going to use the one that has kilograms in it. Okay. Now, I can take this, let me change colors real quick. I can take this and I can write it two ways, right? I can write it as 1 kilogram is 1,000 grams, or 1,000 grams is 1 kilogram. Right? I can do that for the bottom one as well. I'll go ahead. 1 milligram is 10 to the minus 3 grams, or 10 to the minus 3 grams is 1 milligram. Right? I can write that either way. Those are both correct. Those are both exactly the same. The reason being, all these conversion factors are equal to 1. Right? If I go through and show you that here, I'm going to divide both sides by 0.001 gram. And I get a conversion factor on this side. It zoomed in. I got to zoom out. There we go. 0.001 divided by 0.001, that's equal to 1, right? And so all these conversion factors, you're just multiplying by 1, but you're changing units along the way. So if I start with just kilograms, do I need the conversion factor where kilograms is on top or kilograms is on the bottom?
On the bottom.
On the bottom. So I've got 1,000 grams is 1 kilogram. So my kilogram unit cancels, and then I'm left with grams. So do I need the one with grams on the bottom or grams on top?
On the bottom.
Bottom.
On the bottom. So 1 milligram is 10 to the negative 3 grams. Then my gram unit cancels. if you're going to type this into your calculator, be sure that you type 1 times 10 to the negative 3. We tend to leave out that 1 times when we write it out like this, but our calculator is not quite as smart as we are. And so whatever my answer is, the only unit I have left is milligrams. And is it a real big number, a real small number?
Real big.
Real big. Hopefully you got 3,620,000 milligrams, right? The other thing I want to point out here is that conversion factors should never change your number of sig figs, okay? So don't count conversion factors when you do your sig fig analysis. Okay? All right. Any questions about that? Coming up with those conversion factors. Lily.
Do you mind if we don't want to deal with the negative exponents, instead of writing 1 milligram equals 10 to the negative 3rd grams, if we write 1,000 milligrams equals 1 gram and use that in our conversion factor?
I don't mind at all. The reason that I did it this way, let me jump back to our list. The reason I did it this way is because that's how this list does it, right? So it has milli is equal to the 10 to the negative 3. I try to keep it consistent with that. It matters not if you do it as 1,000 milligrams is equal to 1 gram. But I just try to keep it consistent with the table.
Okay, thank you.
Mackenzie?
I just like, how did you get that answer?
Sure. So when I type that into my calculator, I'm going to do 3.62.
Mm-hmm.
Let me erase some things here. We'll be okay, won't we? So in my calculator, I did 3.62 times 1,000, right? I don't need to do this divide by 1 because that doesn't change my answer. I don't need to do this times 1 because that doesn't change my answer. But I need to do divided by 1 times 10 to the negative 3. Now, depending on your calculator, this could be 1e negative 3, right? If your calculator has that little e button, it could be 1 times 10 to the negative 3, right? The important thing here is that if you do it this way, you have to have parentheses around it.
Okay, that's what I did.
Okay, yeah.
Thank you.
A lot of calculators have a shortcut button that doesn't require parentheses, and so it's a little bit cleaner to use. All right. We will save some of these practice problems for tomorrow. It's 12:20. I'll let you go. I will upload this video to Moodle later this afternoon, and you can have access to it there, okay? Any questions before we head out? All right.
No, sir.
Rosie,
Thank
go
you.
ahead. Yeah, Rosie,
Thank you
go
so
ahead.
much.
If
Thank you.
you want to leave, you're welcome to.
Bye.
Thank
Have a
you.
great day.
Is there any homework that we need to know about?
So the only homework that we'll have is in ALEKS, and so as long as you're sort of up to date with your ALEKS stuff, you should be okay.
Okay, so like, I know we went over it last class, but is that just like doing the lessons that it's telling us to do, or is there like a certain checkpoint we're supposed to reach?
So the checkpoint that you should reach is to have the intro units and sig figs at 100%, right? When you log in, and you go to your learning bits. Here, let me get there, and I'll share my screen with you. All right, can you see that, Alex? Yeah.
Yes.
So when you hit start my path, right? This one is a little bit further along than we are currently, but if I go up here, let me do that one more time. Start my path. Click on this little down arrow. Up here, it talks about, it gives us all of the objectives that we have to do. And so if we go to the top, we should have intro units and sig figs. If you're at 100% there, you're done for this week, right? And then, you know, either you can move forward if you want to, or you can wait and do the next part the next week. But by Tuesday at midnight, that should be 100% in order to be done with Alex. Right?
Okay, so you just want us to have the first, like, you want us to have intro units and sig figs completed by midnight Tuesday?
That's right. That's right.
Okay, thank
If
you.
you go to the calendar in Alex, it'll also tell you sort of what is due each. This isn't right. These are not all due Monday. There we go. Yeah, so the intro is due September 8th. I don't know what order this is in, but maybe I shouldn't take a look at the calendar. This is awful. It's very different from the calendar I see. Okay, does that make sense?
Yes, sir, thank
This
you.
is maybe the easiest way to do it. What else can I help you folks with?
That was my question, so I was just staying on to let you
No, no,
answer.
that's good. That's good.
Right, thank you.
Thank you. Have a nice afternoon.
Take care.